Hello, we are Team Teknor Apex and our project is Extruder Heating and Cooling Control. Our technical directors are Mickey Monarch and Brendan O'Reilly. We are comprised of two computer engineers, Ryan Wilkes and Stefano Petrarca, along with two electrical engineers, Brian Bouvet and myself, Samuel Darko. Teknor Apex is located in Pawtucket, Rhode Island, but is an international company that has been providing its clients custom plastics for over 90 years. Currently, they have different models of extruders with different configurations of zones. The temperature is controlled within 10 degrees, and this can create off-grade or defective products as seen on the right. A plastic extruder is made up of zones and a screw. The plastic powder input is then heated to 400 degrees and is extruded as pellets. Each zone is independently controlled and can have different temperature set points. Our anticipated best outcome was to create an adaptable system to control the temperature of an extruder barrel and store historical data. This meant simplifying the human-machine interface and testing to tighten the gains to control the temperature to within 1 degree of the set point. Historical data needed to be compatible with machine learning, and every design choice needed to be scalable. We did not accomplish our anticipated best outcome, but we were able to improve and streamline the user interface, simulate 4 different control loops, and create a historical database. All designs were scalable. Having extruders that are more consistent will create higher quality plastics. The historical data to perform machine learning will increase efficiency and produce exemplary product. Over time, these improvements will save Teknor Apex money by reducing wasted product and lowering electricity bills. In our block diagram, the yellow signifies what the electrical engineers were responsible for, and blue is for the computer engineers. Squares represent what was hardware-based, and circles represent software-based. Several key accomplishments were made implementing and simulating different control loops in ladder logic. 2 of these control loops were the PID and PIDE. PID stands for proportional, integral, differential, and the E in PIDE stands for enhanced. The control loop gains were adjusted to hit the set point as fast as possible with as little overshoot as possible, and then stay at the desired set point. The PID and PIDE simulations both had a start and stop, which left the PID still running in the background for better control. Variance was implemented to mimic real-world temperature disturbances. Friction was added to simulate the heat added by the screw of the extruder. The simulations included both heating and cooling. The final 2 control loops used different gains. The first gain is dead time, or the time of response from when the output changes. The second gain is the time constant, or how long it takes for the slope, also known as the rate of change of the temperature, to reach 66%. The final gain is the maximum rate of change in temperature. In the pseudo temperature integral control and pseudo heat cool simulations, both had an automatic and manual control implemented. They also had an auto start implemented, meaning that the gains described in the previous slide were set automatically. Both control loops feature heating and cooling. Finally, the PID, PIDE, pseudo temperature integral, and pseudo heat cool were all put together and scheduled to run at different times. Up next is Brian.
Hello everyone. I'll be talking about the extruder zone that was shipped to us for the project. We have our section of the extruder barrel shown here, with 2 of the 4 heating elements, here and here. The heating elements wrap completely around the barrel for even heat distribution, and they require 480 volts to operate, which we were unfortunately unable to acquire, preventing us from using them for testing. Also shown in the photo is one of the cooling ports, as you can see here, this little silver piece. These ports allow us to pump water through the core of the extruder barrel. Our cooling system consisted of 2 steel braided hoses that ran from the extruder through a variety of plumbing connections right here. This allowed us to connect a 2-inch hose that was needed to utilize the supplied pump. The cooling system is used for preventing temperature overshoot during the heating loop. As you can also see in the photo, we mounted the extruder between 2 steel plates, securely raising it off the ground. Now moving on to wiring diagrams. The wiring diagrams were created using AutoCAD for this project and give a general representation of some of the hardware to be used, such as input, output, and thermocouple modules. This was accomplished by modifying and connecting wire drawings downloaded from the manufacturer's website. Up next, we have Stefano to talk more about some of the CPE tasks.
Following the work we have accomplished with our PID ladder logic and zone barrel coolant apparatus, I'd like to take this section to discuss how we are managing and monitoring the data output by these systems. Our main monitoring device is a central server computer that we have created from a spare computer. This computer has been set up for remote access outside of campus for us and our technical directors with the assistance of the URI security team. It is installed with all of our important programs between Rockwell Studio 5000 and Inductive Automation Ignition. This is our most optimal setup, as Ignition is designed to be a server-based application gateway with clients remotely accessing it, and this remote access-oriented architecture proved invaluable in the final hours of completing our project. Using Ignition, the server records the live data being fed by the PLC to store in SQL historical databases, which is later processed in generating these histogram reports. These reports plot the relationship between the actual temperature recorded from the zone barrels versus the operator set points, with a secondary graph below showing the heating and cooling activity at those same times. The report's preceding pages are contained with detailed tabulated data of these same trends, and these reports will be generated for each of the control numbers and MOs detailing the zone performance over these 2 respective time spans. These reports are constructed by utilizing many different automation aspects within Ignition. The first is outfitting the tags with the tags that we are interested in with the zone user defined type, or UDT, with historical tracking that stores recorded data into SQL databases. The second is creating a job info UDT that tracks the current control number, which is the current batch out of the MO, or the job number, which the MO itself, and the plastic recipe code, as well as auxiliary tags that pass labeling and data range info into the reports. All of this culminates into our automated delivery system. This is handled by scripts in the control number and MO tags, which are triggered whenever either of their values change. When executed, the script goes through the historical data of each zone in the plastic extruder and generates a report that is exported via an operator's defined method. We have primarily focused on saving to a local domain share or emailing to specific members of your organization. As you can see over here, when saved locally, it also does it in individual folders for each zone. Now I will let Ryan discuss the work we have achieved with our human-machine interfaces.
Here I will talk about the interface part of the project and how it affects the operators through the use of the ignition screens. One of the key accomplishments for the project was to reconsider Teknor Apex's already in use interfaces and reimagine them with more of a focus on the operators. Through research in human-machine interface, HMI, I could focus the point of the interfaces for solely the operators. This was done to quickly convey important information to them. The next implementation was the use of additional alarms in the system to easily inform operators of any errors in temperature and motor performance, and this was for any one zone. Later in the spring semester was a focus on simplifying the user interface. Removing any unnecessary modules helped demonstrate the changes our team made over the months on this project. This simplification involved modifying the HMI design more and removing any testing modules that were set in place for the sake of the project. Finally, the last focus was on the expandability and scalability of the UI. The main focus is on the expansion of multiple zones and in return expansion of the ignition historian, while still keeping focus on the overarching design of the UI. The ignition data storage was also revamped for ease of readability and to easily integrate more of the historian data collection. And with that, I would like to thank everyone that played a part of this project. Our technical directors Brendan O'Reilly, Mickey Monarch, who at the forefront helped with all aspects of the project, Teknor Apex employee Max Reynolds helping on the software side, our consulting technical director Mike Smith, and finally Dr. Harish Sunak, our Capstone program director. Thank you for your time.